Welcome to the second video of week 2, where the main topic is dispersion. In this video, we'll look at the most commonly used measures of variability, the variance and the standard deviation. We'll examine their equations and look at two different ways in Excel to go about computing them. We'll continue working with our example students of Julian and Delia as we do the computations. As you remember, Delia and Julian were both students with the same mean on 20 quiz scores, but different variability, and they had come to a tutor center seeking help. Delia turned out to have a wide range, 15 points, and even a fairly wide interquartile range of 6 points, meaning that sometimes she did very well and sometimes she did very poorly and probably needed help in having a more uniform, good performance. Julian, on the other hand, had a pretty stable range of scores, with only 6 points from his highest to his lowest, and the interquartile range only 3 points wide. So Julian needs to work on something that will boost his consistent performance to a higher level. But we don't have any measure that used all of the scores. Each of these were computed from just 2 scores. One way to make use of all of the data points in the data set would be to look at the average distance from each score to the mean, x minus the mean. But we have the problem, which we saw when we computed the mean, that if we sum up all of those differences, they always sum to 0. It's one aspect of the definition of the mean. So we need to do something so that when we average or deal with these different scores, they won't always add up to 0. And the method that we use is to square those scores instead. So those that were negative, when they're squared, will turn into a positive number. The equation for the variance basically takes the different scores, squares them so that they don't add up to 0, and then adds that result together to produce something that's known as the sum of the squared deviations from the mean, and the abbreviation for that is SS. There turn out to be 2 equations for computing the variance. In general, the one that is for the population is also known as the definitional equation. It's the basic idea behind the variance to square the deviation scores and then average them by dividing by the total number of scores that are in the data set. However, one of the reasons that we'll be computing the variance is to use sample data to estimate the population value. And it was discovered that if we used this definitional equation on sample data, it was consistently underestimating the population parameter. And it turned out that the correct adjustment to fix that is to divide by the sample size minus 1 rather than by the sample size. So our equation overall will have the sum of squared deviation scores on the top part of a fraction, and on the bottom n if we know that we're dealing with the entire population, or in almost every situation in real life, n minus 1 for a sample. If you tried to do those computations by hand, the chances are good that you would make errors. Even with a calculator, the chances of pushing the wrong button are really quite high. So to carry out the steps in that equation, I would use Excel. The way I usually set things up is to look at the equation and then make a column for each step. So I know that I need to begin with the scores, and from each score I'm going to have to subtract the mean. So the first thing I did was to compute the mean using Excel's average function, and then I made a column that had just the mean filled in next to every single score. This let me create a column where I created the difference, x minus the mean, And once I typed that equation into the first cell, I could pull down with that little box in the lower right hand corner, and Excel copied the equation rather than the value all the way to the bottom and carried out the computations. The next thing I did was to create a column for squaring, and I again put the equation in the first cell and then copied all the way down so that the equation was copied for every single cell. Finally, I used Excel's sum function to create that sum of squared deviations from the mean. This last column was score by score, the squared deviation. So when I added them all up, I got the sum. I knew there were 20 quiz scores altogether, so when I took that sum of squared deviations from the mean, represented by the symbol SS, I could divide by 20 to get the variance according to the population equation, or divide by 19 to get the variance according to the sample equation. So it's not so hard to compute the variance, but one of the things that's important to recognize is the fact that we've changed units. Julian's original scores were in quiz points, but the variance, because we squared those deviation scores, is now expressed in squared quiz points. And you can tell right away that that's a unit that doesn't make much sense. So the next thing we're going to do is look at the standard deviation, which is a way of getting back to the original units. The standard deviation is defined as the square root of the variance, which gives us the average linear distance from the mean. Linear because we're no longer in those squared units. The symbol for the standard deviation when we're working with a sample is S. When we're working with a population, it's the Greek letter sigma. So you can see that the equation for the standard deviation is exactly the same as the variance equations, with the addition of the square root symbol around it. Just as a reminder, we had a mu symbol for the mean when we were talking about a population, and now we have sigma or sigma squared for the variance when we're talking about variability. There will be a few more Greek letters as we go about learning statistics, so I encourage you to start to learn the Greek symbols now and to associate them with population parameters, while the Roman digits or Roman letters will always go with sample statistics. As you might imagine, Excel has built-in functions so that instead of going through all of the steps to compute the variance or the standard deviation, we can get there all at one time by using one of the functions. So the steps that we would use to do that would be to enter all of the scores. You can see I've done that for Delia. And I do like to use the named ranges. It's one way of avoiding errors while using Excel. If I drag over a range, there's always the possibility that I stop one too soon, and then I get an incorrect answer simply because I dragged incorrectly. When I use the named range, I can always get exactly the same set of numbers over and over again. So once I've named that range, having correctly dragged over all of them, I can, in a new cell, start to use the function. And I've put the two functions I used in on the screen. If I want the population parameter, I use Excel's function stdev.p for population, and then there's my named range, Delia. If I want it for a sample, the one that has n-1 on the bottom, I get that by using stdev.s and then my named range. And as you can see, the adjustment for the underestimation works. When I'm using this sample equation, I get a value that's slightly larger than the one that I get using the population equation. The Statistics Alive textbook makes quite a to-do over the n versus n minus 1 controversy, and I suppose in theoretical statistics there may be some controversy over this. In real practice, n minus 1 is used very consistently because very rarely in most matters do we have a population. When we have a sample of patients or students or a sample of sales, almost everything that we have is dealing with some sample chosen either randomly or in a convenient way from a population. So although the textbook makes a big to-do and gives you a solid explanation, a better way to think of it is that the equation using n, the population equation, is definitional. It's the way we think about the concept, and then the n minus 1 is an adjustment that we make to the definition to avoid having an underestimate or a biased sample. So the n minus 1 equation gives us an unbiased estimate of the population value. So here's a summary of our measures of variability, which we will put to good use in the upcoming modules in this week. Both the range and the interquartile range are good measures of distance covered by a range of data, but they don't use information from every score. The sum of the squared deviations from the mean, which we often represent as SS, is the aggregate of all the variability in the data set, and we'll see both the term and the abbreviation several times in this course. The variance averages that sum of squares across all the scores, but has the problem of being in squared units. When the scores are a sample, we adjust using n minus 1 in the denominator to avoid underestimating the population variance. The standard deviation is the most useful of all these measures because it's in the original units. In this case, we were dealing with quiz points, and because it's in the same units, we can use it in computations to look at one score in comparison to the whole distribution. And in fact, that's what happens in the upcoming modules that you're studying this week.